For our last video of the section, we'll do a couple of examples that actually state and prove a couple of important facts about linear transformations. First of all, let's recall that a linear transformation, because it's a linear transformation, we know it maps lines to lines. So if the linear transformation is f, its inverse, f inverse, would also map lines to lines. One would go one direction and the other one would take the line back to the other direction where you started. Okay, so let's prove without using coordinates that any linear transformation, f, maps parallel lines to parallel lines. Okay, so if we take two lines that are parallel and then we apply the linear transformation f to them, we will also get two parallel lines. All right, first remember that we only have three examples when we're talking about two lines in the plane. Either the two lines, I'm calling them L prime and M prime, they're the same line, or they intersect when they're not parallel, or the third case is that they are parallel. This is the case we're going to try to prove. So in the proof, we'll just show that this one is impossible and this one is impossible, meaning that they would have to be parallel. Okay, so let's let L and M be two lines that are parallel, where L is parallel to M. Now F is the linear transformation. Let F of L, one of the lines, be L prime, and F of M be M prime. All we have to do is show that L prime is parallel to M prime. We show that must be the case. Okay, so the first thing we're going to do is show that L prime is not the same line as M prime. And we'll use a little one-line proof by contradiction. If L prime and L prime and M prime are the same line, if they are equal, then there are three non-collinear points. Say, for example, take two of them from L, take one of them from M, but you could also take one from L and two from M. It doesn't matter, but they would be three, since they're not all on the same line, they would be non-collinear. So we take three non-collinear points. They map to the same line. L prime and M prime are the same. That means they're mapping to collinear points. So three non-collinear points cannot map to three collinear points. Now that's not permitted by a linear transformation. That's a contradiction. Therefore, we've shown that L prime and M prime are not the same line. Now, let's suppose that they are not parallel. They're two different lines, but they're not parallel to each other. Therefore, if they're not parallel, they intersect. So let's let the point Q prime be that intersection. L prime intersected with M prime. All right. Now, notice we're going to use the inverse function now. Notice that F inverse of Q prime is going to be on the point M and on the point L. That's because F of L is equal to Q prime and F of M is equal to Q prime. So, or is an element of, I should have said. Thus, F inverse of Q prime is an element of L intersected with M. Since it's on M and L, it's on the intersection. Well, that's a contradiction. That means that the line L intersects M. That's a contradiction. Therefore, we've ruled out the two impossible cases. That means that L prime is in fact parallel to M prime, and linear transformations map parallel lines to parallel lines. Okay, last example. Prove that a linear transformation F maps a parallelogram and its diagonals to another parallelogram and its diagonals. Furthermore, prove that the midpoints of line segments are preserved. Okay, so here's how we're going to start. I've already started a couple of the drawings here. Let's draw a segment, AC, this segment here. And let's give it a midpoint of M, like that. And then construct the parallelogram ABCD that has AC as one of the diagonals. So I made some parallel lines here and here. So now I'm going to get A, B, C, D. And I've got a parallelogram and one of its diagonals drawn. Recall the diagonals of a parallelogram meet at their midpoints. We proved that in a previous video. The diagonals of a parallelogram meet at their midpoints. So M, which we'll call the midpoint, right here, we already did label it. M is also the midpoint of BD. M is also the midpoint of line segment BD. All right, now we're going to look at the linear transformation F. Since linear transformations map line segments to line segments, and by using the previous problem that it maps parallel lines to parallel lines, we see that F will map ABCD to another parallelogram. Let's draw it. I've got two parallel lines drawn here of the same length. So let's call this one A prime, B prime, C prime, D prime. So we'll just say, for example, that this parallelogram gets mapped by F into this one. ABCD goes to A prime, B prime, C prime, D prime. Okay, and the diagonals are AC and, I'm sorry, A prime, C prime, and then B prime, D prime. And they meet right there. Okay. Since linear transformations map line segments to line segments and parallel lines to parallel lines, we see that F maps this parallelogram to this parallelogram. It is a parallelogram because AB and DC were parallel, so the transformation will map them to AB and A prime B prime and D prime C prime, which will also be parallel. And likewise with AD BC and A prime D prime B prime C prime. And we have the diagonals, and diagonals of a parallelogram meet at both of their midpoints. And in this one, let's call it N. So N is the midpoints of both of those. So we see that M is the intersection of AC line segment intersected with BD. This is just kind of reviewing what we already did. N is equal to A prime C prime line segment intersected with B prime D prime line segment. Okay, since M is on both of these two segments, these two diagonals, we see F of M is going to be on both of these two line segments. Therefore, F of M is equal to N. That midpoint of the line segments over here, the diagonals, will get mapped to the midpoint of the diagonals over there. And that is sufficient to prove that the line midpoints of segments are preserved. The midpoints of both of these segments become the midpoints of the two segments they get mapped to.